Hello, my name is Paul Geyer, and I will be chatting with you today about an introduction to concrete pavements. This is what I'll be talking about today, the chapters in the book, so to speak. Some comments on the purpose of this discussion, the scope of it. Chapter 3, Responsibilities, Strength, and Air Content. It's important that these be defined in a contract. Chapter 4, Cement. 5, Aggregates. 6, Admixtures. 7, Pozzolans. 8, Miscellaneous Materials. 9, Water. 10, Sampling and Testing of Materials. 11, Delivery and Control and Storage of Materials. 12, Grade Control. 13, Proportioning. 14, Subgrade Base Forms and String Lines. 15, Batching and Mixing. 16, Placing. 17, Field Test Specimens. 18, Finishing. 19, Curing. 20, Grade and Surface Smoothness Requirements. 21, Tolerances in Pavement Thickness. 22, Repairs of Defective Pavement Slabs. 23, Joints. 24, Pavement Protection. 25, Measurements and References. So as you can see from the table of contents, this discussion provides information on the materials and construction procedures for concrete pavements. We are talking only about concrete pavements, not concrete structures. And this discussion describes the constituents to be used in concrete, procedures to be used in manufacturing the concrete, and the equipment and procedures to place, texture, and cure concrete for pavements. Responsibilities are very important in concrete work. The strength of the concrete is, of course, dependent upon the components of the concrete, and the air content is part of the design. The responsibility for mixture proportioning must be clearly assigned to either the contractor or what is called in this discussion the contracting officer. Now, the term contracting officer is used here to indicate the owner's agent on the project, speaking for the owner. And in the real world, he may have other names such as project engineer, field engineer, inspector, etc. In this discussion, the term contracting officer is used to mean the owner's representative on the project, and that's how he is referred to, would be referred to in the contract documents. So when the contracting officer is responsible for mixture proportioning, he needs to approve all concrete materials as well as determine and adjust proportions of all concrete mixtures as necessary to obtain the strength and quality of concrete required for the pavements. Cement is typically a separate pay item in the contract. So if the contracting officer directs that additional concrete be added to the mix, cement be added to the mix, that is paid for on a unit cost basis typically. If the contractor is responsible for mixture proportioning, responsible via the contract documents, he will control all proportions of the concrete mixture necessary to obtain the strength and quality of the concrete required for the pavements, and cement will not be a separate pay, typically not be a separate pay item in the contract, because the contractor will have had the opportunity to consider that in submitting his bid. The contracting officer, however, is typically responsible for approving the quality of all materials the contractor uses in the concrete. The contractor, as part of the approval process, must submit proposed mixtures if he is responsible for mixture proportioning, samples of all materials, and detailed descriptions of all plant, construction equipment, and proposed construction procedures prior to the start of construction. Flexural strength of the concrete is critically important. Structural designs are based on flexural strengths that the concrete is expected to obtain at typically 28 days for road and highway pavements and 90 days for airfield pavements. These ages are not adequate for quality control in the field, since a large amount of low-strength concrete could be placed before strength tests on samples revealed the problem. Correlations can be established between a 14-day strength and the 28 or 90-day strength used in the design, and this correlated 14-day strength can be used as a strength check for a more timely concrete mixture control in the field. Materials and flexural strength are critical items in the concrete. To select suitable flexural strengths for the design of pavements and for inclusion in contract specifications, the contracting officer should have reliable information regarding flexural strengths obtainable with acceptable concrete materials which are available in the vicinity of the project, and the availability of materials in the vicinity of a project is an important consideration. Typical design values for flexural strength of paving quality concrete vary from 500 to 750 pounds per square inch. Numerous tests indicate considerable variation in the flexural strength of concrete when different aggregates or different cements are used. There are some indications that aggregate shape and modulus of elasticity are relatively more important in concrete flexural strength than in compressive strength. Also, after optimum flexural strength is reached, there usually is little increase in strength, even with a large increase in cement contact. Mixture proportioning studies should be made in accordance with ACI, American Concrete Institute, 211.1, to determine the flexural strengths to be used for the design of the project. The water-cement ratio, strength relations for mixture proportioning in ACI 211.1 are given in terms of compressive strength. Table 1 following gives some approximate guidance for relating the concrete modulus of rupture to the compressive strength water cement ratio relationships given in ACI 211.1. All aggregates, cementitious materials, and admixtures used in the mixture proportioning studies shall be representative of materials available for use in pavement construction. In selecting a flexural strength for pavement design, suitable allowances will be made for variations in strength indicated by tests of different combinations of aggregate and cement. Pavement design will be based on a realistic and economical strength obtainable with available materials. Table 1 provides a picture of the approximate relationship between water-cement ratio and strengths of concrete modified from ACI 211.1. Compressive strength, as an example, at 28 days, 6,000 psi. Approximate range of modulus of rupture psi 700 to 800, on up to compressive strength at 28 days of 2000 psi, approximate range of modulus of rupture 350 to 450, and the water cement ratios as for an air entrained and non-air entrained concrete indicated in the last two columns. Selection of a field control strength is important. Once a mixture proportion is selected to provide the required design flexural strength at 28 or 90 days and a correlated 14-day strength is developed from laboratory testing, a field control strength is selected such that 80% of the consecutive 14-day flexural strength test results fall above it. The 14-day field control strength is determined from the formula F sub FC field control, F coordinated minus 0.84 SD. F sub FC is the 14-day field control flexural strength. F correlated is the 14-day flexural strength that is correlated with the required 28 or 90-day strength. And SD is the standard deviation of flexural strength results. If sufficient test results are not available to establish a reasonable standard deviation in the mixture, the coefficient of variation, that is the standard deviation of the mixture flexural strength divided by the mean mixture flexural strength, may be estimated as 10% for large projects with good quality control and 15 to 20% for smaller jobs or jobs with relatively poor quality control. Test specimens are an important tool in the concrete pavement construction process. Flexural strength tests should be made on molded beam specimens 6-inch by 6-inch cross-sectional dimensions in accordance with ASTM C78. Standardization of the test specimen is necessary because of the variations in flexural strength obtained with specimens of different sizes. The 6-inch by 6-inch molded beam specimen must be used for all flexural strength determinations in both the laboratory and the field. Air content is, of course, one of the components of concrete. The effects of air entrainment must be taken into consideration. Air entrained concrete is not required for all concrete pavements. Air entrainment improves the workability and placing characteristics of freshly mixed concrete and is required for the freezing and thawing resistance of hardened concrete. The use of entrained air in concrete will reduce strength, but because of the improved workability in the freshly mixed concrete, adjustments in aggregate proportions and reduction of water are normally possible that will negate or at least minimize the loss of strength. Proper proportioning and control of the air-entrained concrete mixture are essential in order to derive maximum benefits from the improvement in the placeability and durability of the concrete with a minimum effect on flexural strength. The percentage of air content is of importance in the concrete pavement construction process. The specified air content shall be 6 plus or minus 1.5% for concrete pavements located in regions where resistance to freezing and thawing is a prime consideration, and will be 5 plus or minus 1.5% for concrete pavements located in regions where frost action is not a factor and air entrainment is used primarily to improve the workability and placeability of freshly mixed concrete. Air content must be controlled in the field at the point within the specified range most appropriate for local conditions depending upon the severity of exposure and the quality and maximum size of aggregate. If slag aggregate is used, the air content shall be determined by the volumetric method described in ASTM C173. Where the aggregate is of comparatively poor quality or when the maximum size is 1 inches or less, the air content will be controlled at 6 plus or minus 1%. In such instances where resistance to freezing and thawing is not a prime consideration, the air content shall be 5 plus or minus 1%. If further reduction in the air content or the use of non-air entrained concrete is necessary, prior approval from the design engineer must be obtained. Cement content in the concrete is, of course, essential. Either the contractor or the contracting officer may be responsible, in accordance with the contract documents, for mixture proportioning. When the contractor is responsible for mixture proportioning, no separate payment will be made for cement. When the contracting officer is responsible for mixture proportioning, no limits for the quantity of cement contact will be included in the contract specifications. The quantity of cement used per cubic yard of concrete will be determined by the contracting officer, and the cement will be paid for under a separate unit cost bid item. When the concrete proposed for use on a paving project has a cement content of less than 470 pounds per cubic yard, prior approval must be obtained from the design engineer. When concrete proportioning is the responsibility of the contractor and the cement content is less than 470 pounds per cubic yard, the results shall be verified by 2 commercial laboratories prior to submittal. The results of mixture proportioning studies for proposed aggregates and cements and the results of qualitative tests on aggregates and on resulting concretes shall be submitted with requests for approval. The fundamental elements of concrete, of course, are cement, aggregate, water, and perhaps air, and perhaps some sort of admixtures. Of these, the cement is critically important. There are 5 Portland cements designated as types 1 through 5 that are marketed currently. ASTM C150 provides a detailed specification for these cements. Type 1 Portland cement is common or ordinary cement that is supplied unless another type is specified. Type 2 is modified Portland cement that provides moderate resistance against sulfate attack and a lower heat of hydration than type 1 cement. It is common for cement to be manufactured to meet the physical and chemical requirements of both type 1 and type 2 cements. Type 3 cement is high early strength cement. Ultimate strength is about the same as type 1 cement, but type 3 cement has a 3-day compressive strength, approximately equal to the type 1 cement's 7-day strength. The cost of type 3 cement in lieu of types 1 or 2 can normally only be justified when early strength gain is needed to open pavements to traffic, or the high heat of hydration is needed for cool construction periods. Type 4 cement has a low heat of hydration that may be useful in mass concrete, but is not likely to be encountered in pavement construction. Type 5 sulfate resistant cement should be used when the concrete will be exposed to severe sulfate attack. The potential for severe sulfate attack exists when the concrete is exposed to water-soluble sulfate in soil or in water in excess of 0.2% or 1,500 parts per million. The potential for moderate sulfate attack exists for sulfate contents in excess of 0.1 or 150 parts per million. High aluminous cement is known as aluminous or calcium aluminate cement, gains most of its strength in 1 day, has a high exotherm, is resistant to chemical attack, and is a refractory material. When exposed to warm, moist conditions, it will undergo a long-term strength loss. High aluminous cement may find some specialized applications in pavement construction where its rapid strength gain, high exotherm, or refractory properties will outweigh its cost and long-term strength loss. There are also expansive cements designated as types K, M, and S in ASTM C845 that may find some application where concrete shrinkage needs to be minimized or avoided. However, there is little experience with these cements and they will require careful investigation before use in pavement construction. At least one United States manufacturer is actively promoting a slag cement made by grinding iron blast furnace slag. This may be substituted for up to 50% of the Portland cement in a pavement mixture if tests show the required final properties are achieved in the hardened cement. Pre-blended mixes of Portland and Pozzolan type IP and Portland slag cements type IS are described in ASTM C 595 and are acceptable for use in pavements. The contractor will be required to use aggregates from approved sources. If the contractor proposes to use aggregates from an unapproved source, the contracting officer will be responsible for conducting tests to determine whether the proposed aggregates will meet the requirements of the project. Sampling and aggregate delivery costs will be borne by the contractor. The contract specifications will state aggregate sample size, delivery location, and required evaluation time for the proposed aggregates. For small jobs requiring 1,600 cubic yards or less of concrete, all tests for aggregates from an unapproved source will be done by the contractor. Aggregates must generally meet the requirements of ASTM C33. These requirements can be adjusted as necessary to reflect local experience with specific aggregates to ensure economical use of aggregates to meet project requirements. The magnesium or sulfate soundness test, ASTM C88, required in ASTM C33, has not been consistently successful in identifying frost-resistant aggregate. Consequently, if an otherwise suitable aggregate fails this test, it should be further investigated using freezing and thawing tests as described in ASTM C666 or ASTM C682 before it is finally rejected. Similarly, if an otherwise suitable aggregate fails the Los Angeles abrasion test, ASTM C131 or C535, it can be accepted if it has a history of local use showing that it can be processed without unacceptable degradation and that it is durable under weathering and traffic conditions comparable to the project involved. Recycled concrete may, in appropriate circumstances, be used as aggregate. Existing concrete may be taken up, crushed to suitable gradation, and reused as concrete aggregate. It must meet all the requirements for gradation and quality that conventional aggregates must meet. All reinforcing steel should be removed. During crushing, hammer mill secondary crushers tend to produce excess fines and should not be used. The recycled concrete aggregates will not normally require washing unless they have been contaminated with base or subgrade material. If the original pavement that is being recycled is D-cracked, then the concrete should be crushed to a maximum size of 3/4 inch. When crushed concrete is being used as fine aggregate, the inclusion of some natural sand may be required to improve the concrete mixture's workability. Minerals in some aggregates can chemically react with the cement alkalis, resulting in an increase in volume that places the concrete under expansive stresses, which may result in map cracking, pop-outs, strength loss, and concrete expansion. Once started, the reaction and the resulting progressive deterioration of the concrete cannot be stopped. These reactions are generally associated with aggregates containing poorly ordered forms of silica such as opal, chalcedony, chert, or flint, alkali silica mixture reactions. Complex layer lattice and silicate minerals such as gray wax, phyllites, siltstones, or agrolites, sometimes differentiated as alkali silicate reaction, or argillaceous dolomitic limestone, alkali carbonate reaction. A petrographic investigation in conjunction with results of tests in accordance with ASTM C227 for alkali silica expansion and ASTM C586 for alkali carbonate expansion is the most promising approach for identifying these problems. If possible, reactive aggregates should be avoided. If they cannot be avoided, low alkali cement should be specified. If low alkali cement is not available or is overly expensive, some pozzolans and slag cements have been successful in countering alkali silica reactions, or reactive aggregate may be blended with non-reactive aggregate to lessen the effect of the reactions. some discussion of coarse aggregate is appropriate. The composition of coarse aggregate may be natural gravel, crushed stone, crushed recycled concrete, or iron blast furnace slag. The crushing of gravel tends to improve the quality and the bond characteristics and generally results in a higher flexural strength of concrete than if uncrushed gravel is used. When mixture proportioning studies or local experience indicates that a low flexural strength will be obtained with uncrushed gravel, the possibility of obtaining higher strength by crushing the gravel will be investigated. Elongated particles with a width to thickness ratio in excess of 3 may not exceed 20% weight. This requirement attempts to avoid introducing structural planes of weakness in the finished concrete, workability problems associated with an excess of particles of these shapes, and durability problems that may develop if air and water are trapped under flat and elongated particles. The maximum size of the coarse aggregate used in pavement concrete should not exceed 1/4 of the pavement thickness. In no case should the coarse aggregate exceed a 2-inch maximum size. For pavement construction in areas where aggregate pop-outs have been a problem or may occur, the coarse aggregate will not exceed 1.5-inch nominal maximum size. In areas where D-line cracking in pavements has been a problem, limestone aggregates should not exceed 1/2-inch nominal maximum size and should be of low absorption. When the nominal maximum size of coarse aggregate is greater than 1 inch, the aggregate shall be finished in 2 size groups, as shown in Table 2 following, with gradings within the separated size groups conforming to the requirements of Table 3. Where local practice provides size group separations other than those shown in Table 2, local size gradings may be specified if approximately the same size ranges are obtained and the grading of coarse aggregate when combined and batched for concrete is as required by mixture proportioning. For projects requiring 1,600 cubic yards or less of concrete, special grading requirements for coarse aggregate, according to local practice, may be substituted for the gradings shown. Local State Department of Transportation specifications for gradings may be used for those jobs requiring 1,600 cubic yards or less of concrete. Table 2 indicates the coarse aggregate size groups. Table 3 indicates the grading of coarse aggregate. Deleterious substances in aggregates can be an issue. If the pavement is one for an airport or airfield or landing strip, Table 4 lists common deleterious substances and specifies limits for these materials. The performance history of local aggregates contributing to pavement defects will be the determining factor in setting the limits for deleterious substances. The limits are intended to eliminate pop-outs and weather-outs in runways and taxiways. Other deleterious substances known to contribute to pop-outs will be identified by the contracting officer, and suitable limits will be specified. Calcium oxide and magnesium oxide, or a mixture thereof, in lumps representing the hard burned oxides from fluxing stone or refractory brick, should be added to the list of deleterious substances if air-cooled blast furnace slag is used as the aggregate. Since the types of materials producing pop-outs will vary for different areas, some adjustments of the limits may be desirable for individual projects. Reductions in specified limits may be made as necessary, but increases to permit the use of local aggregates that have an acceptable experience record will be governed by special procedures. With other pavements, the limiting amounts of deleterious substances in each size of coarse aggregate will be as specified as indicated in Table 5. Other deleterious substances will be identified by the contracting officer, and suitable limits will be specified and materials defined when necessary. Table 4 indicates deleterious materials in coarse aggregates for runways and taxiways at airfields. Table 4 continued. And Table 5 indicating deleterious materials in coarse aggregates for other pavements. Slag aggregate, such as iron ore blast furnace slag aggregates, vary widely in properties depending on the manufacturing and cooling processes used. Unaged blast furnace slag may contain free lime, but aging reduces this to acceptable levels. Properly aged iron ore blast furnace aggregate has a good history of performance. Slag from steel mills, however, is not acceptable as concrete aggregate because of the various oxides it contains. With regard to fine aggregate, their composition and shape, requirements for composition and particle shape of fine aggregate are purely descriptive. For example, natural and/or manufactured sand, spherical or cubical, and no limits are shown. A limit will be included for flat and elongated particles in fine aggregate comparable with the limit specified for coarse aggregates when tests indicate that poor particle shape will affect the workability and quality of the concrete. The grading and uniformity of grading specified in Table 6 for fine aggregates are desirable for pavement concrete and can generally be met at a reasonable cost within the continental United States. However, if conformance with these requirements will result in undue construction costs, and if investigation of the available sources of fine aggregate in the locality indicates that limits other than specified are desirable, a request should be made to the and submitted to the design engineer. The amount of deleterious substances in the fine aggregate shall not exceed the limits shown in Table 7. Table 6 indicates the grading of fine aggregates. Table 7 indicates deleterious substances in fine aggregates. To avoid inclusion in aggregate for calibration hard stands, the pavement concrete of iron oxides or other iron-rich materials having magnetic properties that will interfere with the operation of the facility, the concrete aggregate proposed for paving calibration hard stands will be subjected to detailed petrographic analyses in accordance with ASTM C295 prior to acceptance. Special attention will be given to the existence of magnetite in granites, high iron minerals in trap rock, pyrite in limestone, and free iron or iron oxide in slag aggregate. When a list of aggregate sources is included in the contract specifications, the sources not approved for concrete used in calibration hard stands will be indicated. With regard to the aggregate for power check pads, concrete that will be exposed to extended jet engine blasts during maintenance can use igneous rocks with a low silica content and a high content of ferromagnesium minerals or slag as aggregate to improve its performance under high temperature. Aggregates rich in silica such as quartzite or chert should be avoided. Aggregate with a high silica content such as sandstone or granite, especially if coarse-grained, can cause problems. Calcareous aggregates such as limestone or dolomite are acceptable. With regard to admixtures are used to modify properties of fresh or hardened concrete. They may be used to improve workability, control initial set, reduce heat generation, accelerate strength gain, increase strength, and improve ductility. 7 chemical admixtures are listed for use in Portland cement concrete in ASTM C494 as follows. Type A, water-reducing admixture. Type B, retarding admixture. Type C, accelerating admixture. Type D, water-reducing and retarding admixture. Type E, water-reducing and accelerating admixture. Type F, water-reducing high-range admixture. And Type D, water-reducing high-range and retarding admixture. With regard to air entraining admixtures, they provide resistance to freezing and thawing and should meet the requirements of ASTM C260 and will normally be required in all concrete for pavements. For small jobs under 1,600 cubic yards, air entraining cements may be considered. The use of any other admixture will depend on the economics of its use and site conditions. The effect of an admixture will vary depending upon conditions such as cement type, specific mixture proportions, ambient temperature, and water quality. Furthermore, an admixture may affect several qualities of the concrete, and some desirable properties may be adversely affected. Consequently, the decision to use an admixture must be based on experience and tests with the cement aggregates and admixtures representative of those to be used on the project. It must be demonstrated that the final concrete proposed pavement quality is not adversely affected by the use of any proposed admixture. More extensive guidance on admixtures is provided in ACI 212.1 and ACI 212.2R. Pozzolans are defined in ASTM CX 618 as siliceous and aluminous materials which in themselves possess little or no cementitious value, but will, in finely divided form and in the presence of moisture, chemically react with calcium hydroxide at ordinary temperatures to form compounds possessing cementitious properties. This ASTM specification recognizes 3 classes of pozzolan and provides detailed requirements for each class. Class N pozzolans are raw or calcined natural positons such as diatomaceous earths, opaline cherts, tuffs, volcanic ashes, clays, and shales. Fly ash is divided into 2 classes. Class F is fly ash produced by burning anthracite or bituminous coal, and Class C fly ash is produced by burning lignite or subbituminous coal. EPA guidelines published in 1983 require that the use of fly ash must be allowed on all federal projects unless it can be proven technically unsuitable. Pozzolans may be substituted for a maximum of 25% by volume of Portland cement and concrete for pavements. If substitution of pozzolan above this limit is contemplated, a thorough test program must show that the proposed substitution limit will not adversely affect workability, admixture, performance strength, and durability of the final concrete. Pozzolans typically have specific gravities appreciably lower than Portland cement, and pozzolan limits are expressed as a percent of the volume of cementitious materials. In general, concrete containing pozzolans has improved workability, lower heat of hydration, and a slower strength gain. When pozzolans are to be used, the required time to gain the design strength may be increased beyond the standard 28 days for roads and streets and 90 days for runways and taxiways at airports and airfields. The Class N pozzolans will not generally be encountered in pavement construction. The use of fly ash, however, is becoming increasingly common. Fly ash produced by industrial burning of coal tends to be highly variable depending on factors such as emission controls, load, and boiler design. This production variability is compounded further by the natural variability of lignite and subbituminous coal that produce Class C pozzolan. Also, Class C pozzolans have poor resistance to sulfate attack, and some have high alkali contents that may contribute to alkali aggregate reaction. Specifications for pozzolans should require that the ASTM C618 specification be modified to require a maximum loss on ignition of 6 and 8% respectively for Class F and Class N pozzolans, and a minimum pozzolanic activity index with lime of 900 psi at 7 days. Mixture proportioning studies should use the same pozzolans and cements that will be used on the project and must require that the final concrete characteristics, strength gain, and durability are adequate. With regard to miscellaneous materials, other materials used in concrete pavement construction include curing materials, dowels, tie bars, reinforcement, and expansion joint filler, and are covered by applicable specifications. When concrete is required to be free of magnetic materials, special instructions are required. Field welding of crossbars, tack welding, is prohibited. All welded splices shall conform to the requirements of American Welding Society AWS-D 1.4. Selection of the proper welding procedure depends on the actual chemical composition of the steel. A procedure suitable for one chemical composition can be totally unsuited for another composition of the same strength grade. It's essential that the composition of the steel to be welded be determined before the welding procedure is established. Where reinforcing bars are to be ordered for new work, the fabricator should be informed that welded splices are contemplated. The fabricator can provide the chemical composition of the reinforcing bars, and in many cases can provide bars that are more suited to welding. Epoxy-coated reinforcing steel and dowel bars are being used more frequently in areas such as bridge decks, coastal areas, and pavements subject to heavy applications of de-icing salts to minimize potential corrosion problems. If these materials are used, they should conform to ASTM A775. Epoxy-coated dowels and reinforcing steel will rest on epoxy-coated wire bar supports or on bar supports made of dielectric material. Wire bar supports will be coated for a minimum of 2 inches from the point of contact with the epoxy-coated reinforcing bars. Adequate ventilation to dissipate fumes must be provided if epoxy-coated steel is welded. Water for mixing concrete must be free from materials that affect hydration of the cement. Potable water may be used without testing. However, tests will be made in accordance with the appropriate standards if the water source is a stream or another body of water of unknown quality. Seawater has been used successfully as mixing water, but this should only be done if there is no feasible alternative. There may be up to a 15% loss in ultimate strength, set times may be affected, and surface efflorescence may occur. The risk of steel corrosion may be increased, so the use of coated dowels and reinforcing steel should be considered if seawater is to be used. The water for mixing concrete shall be free from materials that affect hydration of the cement. Potable water may be used without testing. However, tests shall be made in accordance with the appropriate standards if the water source is a stream or another body of water of unknown quality. Seawater has been successfully used as mixing water. Sampling and testing of materials is important. With regard to the cement to be used in pavements for airports and airfields, traffic will be sampled and tested. Cement meeting all other test requirements may be accepted prior to the required 7-day age when the strength is equal to or greater than the 7-day strength requirement. Cement for pavement projects requiring 1,600 cubic yards or less of concrete may be accepted on the basis of the manufacturer's certified mill test reports showing compliance with cited cement specifications. With regard to aggregates and their listed sources, the listing of aggregate sources shall be based on a thorough investigation to determine that suitable aggregates are obtainable for the purpose and the proposed use. Evaluation of the material will require complete laboratory testing, including petrographic examinations, physical tests, durability tests, and alkali resistivity reactivity tests. The service record of aggregates must be determined by inspecting structures that have had exposure equivalent to the proposed structure. When an aggregate source has been listed previously for use on the basis of a complete investigation, additional similar use of the source within a period of 3 years may be permitted on the basis of petrographic examinations and limited physical tests if the results show no change in the composition and quality of aggregate. For proper design and preparation of plans and specifications, it is necessary to investigate and determine suitable aggregate sources, and concrete strengths obtainable with aggregates. It's essential that these investigations be conducted as early as possible during project planning. When the contract specifications cover the paving of calibration hard stands, the list of sources shall indicate which sources are approved for such work. When the contractor proposes aggregate from a source not previously listed, the evaluation of samples of the aggregate shall include all tests necessary to demonstrate that a concrete produced from the materials will have quality and strength comparable with that of concrete made with aggregate from the approved sources listed. When the contracting officer is responsible for mixture proportioning and the cement is a separate pay item in the contract, aggregates of good quality that require an increase in the quantity of cement over that required by aggregates from listed sources to produce concrete of the specified flexural strength will be approved for use only if the contractor agrees in writing to pay for the additional cement required. When the contract specifications do not include a list of approved aggregate sources, the sources proposed by the contractor will be investigated as soon as possible after the award of the contract. When contract specifications cover the paving of calibration hard stands, the list of sources will indicate which sources are approved for such work. When the contractor proposes aggregate from a source not previously listed, the evaluation of samples of that aggregate will include all tests necessary to demonstrate that a concrete produced from the materials will have quality and strength comparable with that of concrete made with aggregate from the approved sources listed. When the contracting officer is responsible for mixture proportioning and cement is a separate pay item in the contract, aggregates of good quality that require an increase in the quantity of cement over that required by aggregates from listed sources to produce concrete of the specified flexural strength will be approved for use only if the contractor agrees in writing to pay for the additional cement required. When the contract specifications do not include a list of approved aggregate sources, the sources proposed by the contractor will be investigated as soon as possible after the award of the contract. Evaluation of aggregates from non-listed sources and concrete mixture proportioning for projects requiring 1,600 cubic yards or less of concrete, except for airfields, will be performed by an approved commercial testing laboratory. Separate storage facilities must be provided for each type of cementitious material. Storage facilities will be thoroughly cleaned before changing the type of cementitious material stored in it. Storage facilities must be weather-tight and must be properly ventilated. Aggregate handling and aggregate storage facilities may vary greatly for different projects, and only general requirements can be specified. Grading and uniformity of grading requirements will be determined as the aggregates are delivered to the mixer, and the contractor is responsible for meeting these requirements. Careful inspection of storage and handling operations, however, is desirable to assure satisfactory control of the aggregate grading and to prevent contamination by foreign material. Aggregate storage techniques that use coned piles or spread truck dumped aggregate with a bulldozer cause segregation problems. Aggregates delivered by trucks are best dumped and left in individual adjacent piles. A clamshell spreading aggregate in thin layers has also been used to minimize segregation. Aggregate should be handled as little as possible to minimize segregation. Potential sources of contaminants include wind-blown foundation and adjacent materials and contaminants from equipment using in handling the aggregate. Uniformity of free moisture in aggregate is essential for proper control of concrete consistency. A period of free draining storage is required for fine aggregates and the smaller size of coarse aggregate. Normally 24 to 48 hours will be sufficient. However, shorter or longer times may be specified if the tests of time to reach an equilibrium so indicate. The lines and grades shown for each pavement category of the contract shall be established and maintained by means of line and grade stakes placed at the job site by the contractor. Elevations of all benchmarks used by the contractor for controlling pavement operations at the job site will be established and maintained. The finished pavement grade lines and elevations shown shall be established and controlled at the job site in accordance with benchmark elevations furnished by the contracting officer. The pavement shall be constructed to the thickness and elevations indicated. Provisions for line and grade control for roads, streets, and open storage areas shall be included in the contract specifications. Before any concrete is placed, trial mixtures shall be prepared with materials from the sources to be used for production of concrete on the project. When the contractor is responsible for mixture proportioning, trial mixtures shall be prepared by a commercial testing laboratory approved by the contracting officer at no additional expense, and the results shall be submitted to the contracting officer for approval. When the contracting officer is responsible for mixture proportioning, trial mixtures will be prepared by the contracting officer with materials supplied by the contractor from the sources to be used for production of concrete on the project. Mixtures will be made in sufficient number to establish optimum proportions of the aggregates and to represent a wide range in cement contents and water cement ratios within specified requirements for air content and workability. The water cement ratio will not exceed 0.45 by weight for pavement mixtures. After the final proportions of the trial mixtures have been established, 6-inch by 6-inch cross-section test beam specimens from each mixture will be made in accordance with ASTM C192 and tested as described in ASTM C78. A minimum of 9 test specimens should be made to establish the flexural strength of each mixture at each test stage. From these mixture proportioning studies, the controlling maximum water cement ratio and hence the cement content required to produce concrete of specified strength will be determined. The same procedure will be used to establish new mixture proportions when necessary because of a change in the source or the character of the concrete ingredients after concrete placement has started. When the contracting officer is responsible for mixture proportions of all materials used in the concrete mixture will be as directed. The contracting officer will require such changes in the mixture proportions as necessary to maintain the workability, strength, and quality required by the contract specifications. The mixture proportions determined by mixture proportioning studies will be used in starting paving operations. Adjustments will be made by the contracting officer as necessary to establish the mixture proportions best suited for job conditions and materials used. Subsequent mixture adjustments will be made when necessary, but usually these adjustments will be of a minor nature as required to compensate for variations in gradings and the moisture content of the aggregate. When the contractor is responsible for the mixture proportions of all materials used in the concrete mixture will be as directed by the contractor. The contractor will require such changes in the mixture proportions as necessary to maintain the workability, strength, and quality required by the contract specifications. The mixture proportions determined by mixture proportioning studies will be used in starting paving operations. Adjustments will be made by the contractor as necessary to establish the mixture proportions best suited for the job conditions and materials used. Project specifications will require the contractor to notify the contracting officer prior to making any change to the approved mixture proportions and to indicate the changes to be made. Changes to the mixture proportions will be of a minor nature as required to compensate for variations in gradings and the moisture content of the aggregate unless laboratory mixture studies for the new mixture are submitted for approval. The concrete slump shall not exceed 2 inches. Within this maximum limit, the slump will be maintained at the lowest practical value suitable for prevailing weather conditions and for equipment and methods used in placement of the concrete. For small paved areas, slump in excess of 2 inches may be permitted, but in no case will the slump be allowed to exceed 3 inches. The concrete slump will be determined in the field by the method specified in ASTM C143. Slump for slip-form paving shall be specified in a range of 0 to 1¼ inches. Control of the strength of the concrete mixtures shall be based on tests of concrete specimens taken during the paving operations. Pavements to be used by aircraft are designed on the basis of flexural strength that the concrete is expected to attain at 90 days, and specimens will be tested at this age for use in the evaluation pavements. Since the period necessary to obtain the 90-day field strength is too great to exercise proper control of the concrete during pavement construction, a 14-day strength requirement will be included in the contract specifications. Flexural strength tests will be made at 14 days to determine compliance with the 14-day strength requirement. In addition, 7-day strength tests will be made to provide an early indication of the concrete strength. The average strength at the age of 14 days of any 5 consecutive individual test values representing each concrete mixture will be not less than the specified strength at the age of 14 days, and not more than 20% of the individual values will be less than the specified strength. Adjustments of the concrete mixture proportions will be made as necessary to maintain the strength control. When sufficient 90-day strengths become available, further adjustment of the concrete mixture may be made as necessary to assure that the 90-day strength used for the design of the pavements will be obtained and that an economical mixture is being used. The setting and protection of forms and string lines and the final preparation of the subgrade base course or filter course requires close attention to all details to assure that the pavement will have the required thickness and the surface will bear the required grade. Subgrade is the natural soil or fill upon which the base and concrete pavement are placed. Special procedures may be necessary when dealing with frost-susceptible soils, expansive soils, pumping susceptible soils, laterific soils, or organic soils. Removing soft or troublesome soils that occur in pockets may be desirable where possible. A base may perform many functions such as drainage, construction platform, and structural strengthening of the pavement. A base may be a granular material or lime, cement, or an asphalt stabilized material. Also, a lean concrete, sometimes referred to as econocrete, is sometimes used as a base. There is no clearly accepted definition, but cement contents are typically lower and sometimes poorer quality aggregates are used. The lean concrete base should meet the strength and durability requirements of cement stabilized materials and can be treated as a high quality stabilized material in design. Steel forms will be used for all formed pavement construction. Wood forms generally are unsatisfactory for paving work, and their use will not be permitted except for such miscellaneous areas as bulkheads and curved fillets. To avoid the excessive cost of pavement construction for small jobs, wood forms may be allowed for pavements less than 8 inches thick in non-critical areas such as open storage areas, parking pads, and vehicle parking. Provisions relating to built-up forms may be omitted from contract specifications when the contract plans require constant slab depth for each paved area. When this provision is retained in a contract specification, the contractor is required to furnish steel forms equal to the edge thickness of the majority of pavement slabs for each paved area. Built-up forms will be used only where edge thicknesses exceed the basic form depth. The base width of built-up forms will be equal to the width required for a comparable full-depth form. Side forms on slip form pavers will be the full depth of the pavement. Forms and string lines should be installed well in advance of concrete paving operations so that the required checks and necessary corrections can be made without stopping or hindering concrete placement. The same reasoning applies to the final preparation of the underlying material, which should not be less than 1 day's operation of the paving equipment ahead of paving. The string line will be of high-strength cord or wire. The choice will depend on the type of automatically controlled slip-form paver used. Certain manufacturers recommend that high tensile strength wire be stretched tautly between supports. Other manufacturers recommend a large diameter cord and do not require the tautness that is recommended for the wire. The use of wire requires firmly anchored supports. As a result, the wire is less likely to be disturbed than is the cord, whose supports do not have to be so firmly anchored. The wire is difficult to see, and flagging should be attached between the supports to reduce the chance that it will be disturbed during construction. The cord does not require supports to be as firmly anchored as for the wire, and as a result the cord is easier to install and maintain. However, the chance of sagging between the supports is greater. The cord is easy to see, and as a result the chances of its being knocked out of alignment are less than for the wire. However, the cord is more easily disturbed than the wire and should be checked frequently. Pavement forms generally may be removed 12 hours after the concrete is placed. A longer period will be necessary when the strength gain of the concrete is retarded because of delayed or inadequate protection during cold weather. In some instances, earlier removal of forms may be permitted so that the transverse joints may be sawed completely through to the edge of the slab without leaving a small fillet of concrete adjacent to the form. There are three types of batching and mixing plants: automatic, semi-automatic, and manual. For paving projects, either automatic or semi-automatic plants will be acceptable. Specifications will be prepared to allow either type of plant, and the contractor will have the option as to the type of plant to be used. The capacity of the plant to be specified for the batching plant and mixing equipment will be determined in accordance with the concrete placement requirements for the project. Since the pavement slabs are comparatively small, the plant capacity generally will not be influenced by any requirements for maintaining the concrete in a plastic condition during placement. The main considerations will be the required placing schedule to meet the completion date for the construction, or when slip form pavers are used, the required amount of concrete to maintain a uniform forward movement of the paver of not less than 2.5 feet per minute. However, the placement rate specified for pavements constructed during hot weather should also be considered in determining plant capacity requirements. Mixers having a capacity of at least 5 cubic yards of mixed concrete are required for airfield paving projects, but smaller mixers may be permitted for small road projects and other small miscellaneous construction. Contract specifications for jobs of suitable size and location will include an option for the contractor to reduce mixing time during progress of the work from the mixing time required at the start of the job on the basis of mixer performance tests. This table indicates the test requirements for batching and mixing. In addition, no reduction in mixing time will be allowed if it results in a reduction in the 7-day flexural strength from the average strength of 5 consecutive sets of specimens made from batches mixed the full time. The requirements for stationary mixers and truck mixers will be included unless it is determined that concrete complying with the specifications cannot be manufactured by these types of mixers. Truck mixers often have difficulty in discharging the comparatively low slump concrete mixtures required for some pavement construction. Therefore, truck mixers should comply with ASTM C94. The tendency of the concrete to hang up in discharge chutes may cause delays, which frequently lead to requests by the contractor that the concrete slump be increased. This difficulty also may occur with vehicles used for hauling concrete to forms when stationary mixers are used. The slump of ready-mix concrete will not be increased because of the inadequacy of the mixing or transportation equipment to mix and discharge the concrete. Before truck mixers or stationary mixers are approved for use, careful consideration must be given to the proposed plant and facilities for storage and handling of materials, and for batching, mixing, transporting, and handling of concrete at the job site to assure that adequate control of the concrete can be exercised. When truck mixers are used with a long haul between the batching plant and the project, adequate control of the concrete may be difficult due to variations in slump and air content caused by differences in mixing time. In such cases, it will be necessary to require that mixing be done after the trucks arrive at the site. Truck mixers will not be permitted for mixing concrete on slip form construction. Truck mixers shall be equipped with accurate revolution counters. In general, truck mixers should only be used on jobs requiring 2,500 cubic yards or less of concrete. Concrete may be placed between fixed forms or using approved slip form paving equipment. Both methods produce satisfactory results, and when possible, the option should be left with the contractor as to the method to be used. With slip form equipment, the rate of placement can be significantly increased over the rate with fixed forms. In addition, the material for forms and the labor for setting forms are eliminated. As a result, the cost for large jobs will be less for slip form placement than for placement with fixed forms. However, on small jobs or larger jobs with special requirements, the use of fixed forms may be necessary or may be more economical than the use of slip form equipment. No guidelines can be given as to what size job will permit the economic use of slip form pavers. Concrete will be placed before obtaining its initial set and within 45 minutes after cement has been added to the batch. These provisions apply to all paving projects regardless of the type of mixing equipment used. The addition of water to the mixture in excess of that required by the mixture proportions to maintain slump during prolonged mixing will not be permitted. Approval of the slip form paving equipment for airport and airfield pavements will be based on satisfactory performance in the field. Trial sections of sufficient length and located in low-volume aircraft traffic areas will be used to approve the paving equipment, considering both slip form and another for the fill-in operation when scheduled by the contractor. Furthermore, approval shall be based on the ability of the machine to consolidate the concrete and form the pavement to the desired cross-sections. Plan grade and surface smoothness tolerances must be met. Particular attention should be paid to the ability of the machine to form the required edge without excessive slumping or tearing during slip form operations, and to form a suitable longitudinal construction joint during fill-in operations. The machine shall not damage the surface or edge of the previously placed slab during fill-in operations. The suggested length of the trial section is 1,000 to 2,000 feet. Slip form pavers with a full width auger are recommended. Traveling blades have been found to be less satisfactory. If the slip formed pavement is 10 inches or greater in thickness, some of the lighter slip form pavers may have problems properly handling the low slump concrete. Hand spreading of concrete will be permitted only when necessitated by odd widths or shapes of slabs or in emergencies such as equipment breakdown. Vibration requirements are influenced by many factors such as the type and size of aggregate, mixing proportions, air entrainment, slump, workability of mixture, and pavement thickness. The specified maximum spacing for vibrator units and the specified vibrating procedures are based on field experience with the vibration of pavements 12 inches or more in thickness. There has been only limited use of internal vibration for thinner slabs. If necessary for proper consolidation of the concrete, a closer spacing of vibrator units will be required. Particular attention should be paid to vibrators along the edge of the paving lane to assure that the edge is properly consolidated. General experience has been that it is more satisfactory to use vibrators at a closer spacing and for shorter periods of vibration than to attempt to consolidate the concrete by prolonged vibration at a wider spacing. The duration of the vibration will be limited by the time necessary to produce a satisfactory consolidation of the concrete, and over vibration will not be permitted. Vibrators must not be permitted to touch forms, dowels, tie bars, or other embedded surfaces. Surface vibrators will not be permitted because past experience with them has been generally unsatisfactory. Surface vibration tends to bring excess fine material and water to the surface, which in many instances contributes to surface deterioration and scaling. Surface vibrator pans also tend to ride on high places in the concrete surface and thus cause non-uniform consolidation of the concrete. Project drawings will show typical details of all slab reinforcement and will indicate the pavements requiring reinforcement and the location and amount of steel required in the slabs. This information will supplement the specification requirements for reinforcement, and all requirements will be carefully checked to ensure no discrepancies between drawings and specification requirements. Pavement should not be placed when the air temperature is below 40 degrees Fahrenheit. If unusual job conditions require construction at these low temperatures, special provisions for placement and protection of the concrete will be needed. For additional information on winter concreting, refer to ACI 306R. The necessary covers and other means of protecting the concrete during cold weather should be available on the job before starting concrete placement. Calcium chloride as an admixture may be either required or approved to accelerate the setting time of concrete placed during cold weather. No changes will be made in the requirements for temperature of the concrete when placing or for protection of the concrete against freezing when calcium chloride or any other accelerator is used. During hot weather, special precautions are necessary to prevent the formation of plastic shrinkage cracks, which result from an excessive loss of moisture from the concrete before curing is begun. The concrete needs to be placed in the coolest temperature practicable, and in no case should the temperature of the concrete as placed exceed 90 degrees Fahrenheit. Mixing and placing of concrete will be controlled to keep moisture loss at a minimum. Aggregates will be moist when added to the mixer and the subgrade dampened so it will not absorb water from the concrete. The temperature of the concrete may be reduced by using cement with a lower temperature, by sprinkling the stockpiles of aggregate to produce cooling by evaporation, by pre-cooking mixing water, and by avoiding delays in mixing and placing concrete. The concrete needs to be placed and finished as rapidly as practicable and the curing started without delay. If the application of the curing medium should for any reason lag placement for a time sufficient to permit surface drying, the surface should be kept damp with a fog spray and placement should be discontinued until corrective action can be taken. The fog spray equipment will be capable of applying a very fine mist to the concrete to replace moisture lost by evaporation. In windy areas, screens may need to protect the concrete from rapid evaporation caused by wind. Steps shall be taken to avoid an evaporation rate in excess of 0.2 pounds per square foot per hour. This is adequate for most conditions, but there are reports of plastic shrinkage cracking occurring under adverse conditions when the indicated evaporation rate was as low as 0.15 pounds per square foot per hour. Additional information is available in ACI 305R. For small areas such as vehicular parking and paving projects of 1,600 cubic yards or less, machine spreading, finishing, and floating will not be required if the benefits derived from the use of equipment are not commensurate with the cost of using the machines. In these cases, hand spreading and finishing and floating will be specified. Where overlay pavement construction is required, contract specifications will contain special provisions for preparation and treatment of the existing surface before placing concrete in the overlaid pavement. Criteria herein pertain to construction of rigid overlays on existing rigid pavement. Construction of rigid overlays on existing flexible pavement or on existing rigid pavement with a bond-breaking course is treated as new construction. Overlay pavements generally are designed on the assumption that a partial bond will develop between the two concrete layers. Concrete surfaces to receive partially bonded overlays will be thoroughly cleaned of dirt and other foreign material, loose or spalled concrete, extruding joint seal, bituminous patches, and material that would break the bond between the concrete layers. Different areas of pavement will require different treatment. The condition of the existing pavement will determine the cleanup measures necessary. Normally, sandblasting or surface abrading equipment will be required to remove material adhering to the surface, and hand scaling of loose or spalled material will be required. No special treatment such as an acid wash of the prepared surface or the use of a grout bonding course will be required for partially bonded overlays. In areas where oil or grease is present on the surface, scrubbing with a detergent and a wire brush may be required. Cleaning of surfaces to receive the overlay with rotary grinding equipment will be permitted, but the surface must be swept clean prior to placing the concrete overlay. Considerable difficulty has been experienced with uncontrolled cracking of overlay pavements at contraction joints. This cracking is likely to occur during hot weather when the temperature of the existing pavement is appreciably higher than that of the concrete being placed in the overlay. Contraction due to cooling of the base pavement leaves in movement at the existing joint, which may start a crack in the bottom of the overlay as the concrete hardens. This cracking may occur when the concrete is too green to saw. Often the crack is not visible at the surface of the pavement when the sawing is done. To prevent such cracking, it may be necessary to use inserts in the plastic concrete to form contraction joints. Occasional problems have developed when relatively thin concrete pavement has been placed directly on lean concrete bases or stabilized bases with high cement contents. Uncontrolled contraction cracks in the base material have on occasion reflected through the new pavement. If a thin pavement is less than 9 inches thick and is to be placed directly on a cement stabilized or lean concrete base, it may be desirable to either place a bond breaking material between the pavement and base or to saw cut contraction joints in the base to match those in the pavement surface. If a bond breaker is used between the pavement surface and the base, the design engineer must be aware of the lack of bond, since this can affect the required design thickness of pavement. If contraction joints are to be sawed in the base to control cracking, it must be done at an early age for concrete pavements. Field tests other than those called for by contractor quality control will be conducted by the contracting officer to determine the slump and air content of freshly mixed concrete, and specimens will be molded to test for flexural strength of hardened concrete. All tests will be performed under the supervision of the contracting officer. However, since the contractor will be required to furnish concrete samples, labor, and facilities for molding and curing test specimens, specifications must indicate the extent of testing required. Equipment for making air content and slump tests will be furnished by the contracting officer when the owner is responsible for testing, and by the contractor when the contractor is responsible for testing. Beam molds will be made of steel and will be rigid and watertight. Beam molds will be supplied by the contracting officer, except when the contractor is responsible for testing. When molds are required to be furnished by the contractor, details necessary to assure that the bonds molded furnished are satisfactory and will be in the contract specifications. Tests include specimens for determining conformance with specified strength requirements and will be moist cured under field laboratory conditions. The size and number of curing tanks will depend on the number of specimens taken and the ages at which the tests are made. For airfield paving projects, flexural strength tests will be conducted at the ages of 7, 14, and 90 days. For other pavements designed on the basis of 28-day flexural strengths, the test ages will be 7, 14, and 22 days. Where 90-day flexural strength tests are required, provisions will be made for curing and testing of specimens after the project is completed. Ordinarily, no field-cured specimens will be required. However, for cold weather construction, when field strength data may be necessary to permit the opening of the pavement or portions thereof to construction traffic prior to 14 days, test groups of at least 3 beams shall be taken as required from concrete placed in designated areas. The beams of each test group shall be made from a single batch of concrete and shall be cured in accordance with ASTM C31. With regard to finishing and equipment and methods, the types of finishing equipment other than conventional equipment may be used on a trial basis when capable of finishing concrete of the quality and consistency required. Equipment that fails under trial to perform in a satisfactory manner will be rejected and removed from the work area. Finishing operations are designed to obtain a dense, smooth surface true to the required grade. Since the surface receives the greatest exposure to weathering and traffic, every precaution will be taken to obtain a high-quality concrete at the surface. The finishing operations will be kept to the minimum necessary to obtain the required surface finish. Excessive surface manipulation will not be permitted because it tends to bring a surplus of mortar, water, and undesirable soft materials to the surface, which contributes to scaling and surface deterioration. Finishing should leave the surface at the proper grade. If the mechanical finishing operations are properly controlled, very little hand finishing will be necessary. Short floats will be used only as necessary to correct local surface unevenness. Straight edges of the required length will be used primarily to smooth and check the surface. To avoid later costly corrections of hardened pavement which fails to conform with specified surface tolerances, the surface will be thoroughly checked during the mechanical floating and necessary corrections will be made. Machine finishing is required and hand finishing is only permitted for odd widths and shapes of slabs, areas adjacent to headers, and areas around outlets in the pavements. Hand-finished areas will have the same quality and the same surface characteristics as those areas finished by machine. Hand finishing along the edges of slip-formed lanes to correct edge slumping or to repair areas damaged by tearing or sloughing shall be held to a minimum. The only manipulation permitted along the edges of slip-formed lanes shall not disturb the edge or use the edging tools to correct deficiencies in the edge. With regard to surface texture, the final surface texture of the pavement will be provided by means of a burlap drag, broom, artificial turf, wire comb, or grooving. Dragging the surface of the concrete in the direction of concrete placement with moist burlap leaves a fine sandy surface that is adequate for low-speed traffic. At least 2 feet of burlap must be in contact with the concrete, and the burlap shall be cleaned as necessary. An improved skid-resistant surface can be produced with a broom consisting of multiple rolls of stiff bristles capable of producing serrations 1/16 to 1/8 of an inch deep. The brooms will have to be cleaned frequently during texturing. Artificial turf has been used successfully for texturing concrete. This is applied in the same manner as the burlap, with at least 2 feet of the artificial turf in contact with the concrete. One artificial turf that has provided a satisfactory texture consisted of 7,200 polyethylene turf blades, approximately 0.85 inches long per square foot. The wire comb provides the most skid-resistant texture of the finishing techniques described so far. However, it is also the most difficult to use, and adjustments to the concrete proportions may have to be made to find a mixture that can be wire combed without objectionable surface tearing. The wire comb should consist of flexible steel spring lines spaced not less than 1/2 inch nor more than 1 inch apart. Closer spacing causes problems with raveling, and wider spacing results in objectionable road noise. The serrations left by the steel lines should be about 1/8 to 1/4 inch deep and 1/16 to 1/8 inch wide. A single pass of burlap or artificial turf can be made before the wire comb if desired. With regard to curing and first control of cracking, plastic shrinkage cracking is caused by a combination of 1. High ambient air temperature, 2. High concrete temperature, 3. Low relative humidity, and 4. Wind velocity. These conditions need to be controlled when placing and protecting young concrete. It is essential that concrete be protected against the loss of moisture and rapid temperature change for the specified period of protection. All equipment, material, and supplies for adequate curing and protection of the concrete must be on hand and ready to install before actual concrete placement begins. In general, curing will be accomplished by using a pigmented membrane curing compound. However, other methods may be specified if indicated by local conditions. With regard to membrane curing, the curing compound will be applied by means of a power-driven machine straddling the newly paved lane and operated so that the spray will cover the pavement surface completely and uniformly. Spray nozzles must be surrounded by a hood to prevent wind from blowing the curing compound spray. The rate of advancing and spacing of nozzles of the spraying machine will be controlled so that a two-coat overlapping coverage will be provided. Hand-operated pressure sprayers will be permitted only on indicated odd widths and shapes of slabs and on concrete surfaces exposed by removal of forms. The curing compound must form a continuous void-free membrane and be maintained in this condition throughout the curing period. Unsatisfactory or damaged areas will be resprayed. Any damage to the membrane during the sawing operation will be corrected by respraying. When forms are removed, the exposed faces of the concrete will be sprayed with a curing compound. Where it has been established from past experience in an area that membrane curing alone does not adequately protect pavement from shrinkage cracking, a combination of moist curing and membrane curing may be specified. In selecting curing material for pavement surfaces to be painted, consideration shall be given to the necessity of sandblasting to remove coatings and deposits that interfere with the bonding of paint. Curing compounds of the low melting point wax-based type tend to penetrate concrete and should not be used in the areas to be painted. With regard to grading and surface smoothness requirements, first as to pavements for airfields, runways, taxiways, heliports. The specified grade and smoothness requirements applicable to airfield and heliport pavements are shown in Table 8 below. The finished surfaces of airfield and heliport pavements shall have no abrupt change of 1/8 inch or more and shall not deviate from the testing edge of an approved 12-foot straight edge more than the tolerance shown in Table 8 below. For road, street, and open storage concrete pavements, pavements shall be smooth and true to grade in cross-section. When tested with a 10-foot straight edge on lines 5 feet apart, parallel with the center line of the pavement, the surface shall not vary more than 1/8 inch from the testing edge of the straight edge. With regard to requirements for other vehicular parking or vehicular pavements, parking areas, motor pools, and motor storage areas, repair yards, and open storage area pavements shall be smooth and true to grade in cross-section. When tested with a 10-foot straight edge on lines 5 feet apart, parallel with and at right angles to the center line of the paved area, the surface shall vary not more than 1/4 inch from the testing edge of the straight edge. With regard to slip form paving edge slump is the downward movement of the plastic concrete that occurs when the sliding form passes. Excessive slump is indicative of improper concrete mixture proportioning. If the concrete mixture cannot be redesigned to overcome the edge slump problem, fixed form paving shall be used. When slip form paving is used, 85% of the pavement will not have an edge slump exceeding 1/4 inch, and 100% of the pavement will not have an edge slump exceeding 33/8 of an inch. The area of pavement affected by this slump will be limited to the outer 18 inches adjacent to the slab edge. With regard to tolerances in pavement thickness, pavement will be constructed to thicknesses indicated, and pavement thickness will be checked by measurements of cores drilled from the pavement as required by the contracting officers. Cores generally will be taken at intervals of 2,000 feet or a fraction thereof from each pavement lane of paved area where the lanes are 1,000 feet or more in length, and from every other lane of the paved area where the lanes are less than 1,000 feet in length. Additional core drilling to determine the extent of a pavement area deficient in thickness will be included in the contract specification. Cores for checking pavement thickness will have a diameter of no less than 4 inches. When cores are used for compressive strength or splitting tensile strength tests per ASTM C496, as well as for checking pavement thickness, a 6-inch diameter core shall be drilled. Drilling and measurement of cores for checking pavement thickness will be done as directed. Costs of drilling and testing additional cores requested by the contractor will be borne by the contractor. When the contractor is required to cut cores to check pavement thickness, additional core drilling requirements will be included in the contract specification. All core measurements will be made by the contracting officer, and the cores will become the owner's property. With regard to repairs of defective pavement slabs, grooving and sealing or epoxy sealing of random cracks, filling of non-working contraction joints, repairing of spans along joints and cracks, and removing and replacing of broken slabs that occur in non-reinforced concrete pavements during construction will be accomplished according to the requirements in the contract specification. Areas not meeting smoothness and grade requirements will be repaired or replaced. High areas can be reduced by rubbing the freshly finished concrete with carborundum brick and water within 36 hours of the concrete placement, or by grinding the surface after it is 36 hours old. Generally, grinding shall not exceed 1/4 inch in depth. The final surface of the repair area must retain the required skid resistance of the surrounding pavement. With regard to joints, generally, joints are constructed in concrete pavement to permit contraction and expansion of a pavement without irregular cracking, and as a construction expedient to separate the paved area into strips necessary for handling and placing of concrete. There are 3 general types of joints: construction, expansion, and contraction. With regard to construction joints, first, longitudinal construction joints. These joints formed between paving lanes at the spacing indicated will be either thickened edge, keyed and tied, or doweled. The dimensions of the keyed joint are critical. It is essential that both key dimensions and the location of the key in the joint conform with details on drawings. Key dimensions are based on pavement thickness, with each thickness requiring a different key size. When stationary forms are used, metal molds for forming the keyway will be securely fastened to the concrete forms so that molds will not be displaced by paving operations. When slip form pavers are used to form keyed joints, the keyway shall be formed by means of preformed metal keyway liners, which are inserted during paving. The metal liners may be shaped as they are fed through the paver from continuous strips, or they may be preformed sections bolted together before insertion through the paver. It is recommended that the metal liners be left in place. When slip form pavers are used to form keyed and tied joints, bent tie bars shall be inserted into the plastic unconsolidated concrete through a metal keyway liner as described above. The key bars, the tie bars, shall be straightened after the concrete has hardened. The bent bars shall be inspected to ensure that the radius of curvature at the bend is equal to or greater than the specified minimum radius of curvature for the grade of steel being used. When stationary forms are used, all dowels will be placed by the bonded in place method. Either one-piece dowels or split dowels of the threaded type will be used. Dowels will be held accurately and securely in place by fastening to the forms. When slip form pavers are used, dowels shall be placed by bonding the dowels into holes drilled into the hardened concrete with rotary core type drills that can be maintained in a position parallel to the surface of the pavement and perpendicular to the face of the edge of the slab in a longitudinal direction. Some low impact energy hydraulic and electro-pneumatic drills have been used to successfully drill dowel holes without spalling the concrete. These and similar types of drills can be allowed if the contractor is able to satisfactorily drill the specified holes without undue spalling around the hole. The diameter of the hole shall be larger than the diameter of the dowel bar, but should not be more than 1/8 inch larger than the diameter of the dowel bar. The contractor will be required to demonstrate to the contracting officer that the dowels can be securely bonded and proper alignment can be obtained. Continuous inspection will be required thereafter to ensure the dowels are securely bonded and that they are aligned properly both horizontally and vertically. The method used for inserting the epoxy resin grout into the hole shall place sufficient grout to completely anchor the dowel. In the case of transverse construction joints, when concrete placement is stopped or interrupted for 30 minutes or longer, these joints are installed across the pavement lane. Insofar as practicable, these joints will be installed at the location of a planned joint. With regard to expansion joints, when expansion joints are required within a pavement, joint assemblies supporting both joint filler and dowels will be installed before placing concrete. Accurate location and alignment of joint filler and dowels are necessary for proper functioning of joints. Since checking of embedded items in joints installed within a paving lane is extremely difficult, it is essential that assemblies used for supporting embedded items be rigidly constructed and capable of resisting all movement and distortion during paving operations. Great care and continuous inspection are required during placing and finishing of concrete near joints to avoid displacement of joint filler and dowels. Additional hand vibration will be required around the joint assemblies to assure adequate consolidation. The contractor is required to provide a template for checking the position of the dowels. With regard to contraction joints, generally contraction joints use a groove to form a weakened plane in the concrete as the concrete undergoes shrinkage. A fracture forms through the concrete below the groove. Load transfer is provided by aggregate interlock in the fracture plane below the joint groove or by an aggregate interlock and dowels. Where dowels are required across transverse contraction joints, suitable dowel supporting assemblies will be used and care taken to assure proper alignment of dowels in the completed pavement. Requirements for dowel supports have been discussed. Where tie bars are required in longitudinal contraction joints, suitable supporting devices will be provided for holding tie bars in place during paving operations, or the bars may be installed in front of the paver by insertion into the unconsolidated, freshly placed concrete. The device for inserting the bars shall be mounted on the paver and will automatically insert the bars to the specified depth and at the required spacing. With regard to joint types, contraction joints may be constructed by sawing a groove in a hardened concrete or installing a suitable insert in freshly placed concrete. Inserts will not be used on airfield pavements without prior approval. Sawing of joints eliminates manipulation of freshly placed concrete after placement and provides the best conditions for obtaining a smooth surface at the joint. However, sawing time is critical and cracking will occur at the wrong place if the joints are not sawed at the proper time. The filler type joint forms a weakened plane in the freshly placed concrete, which induces fracturing of concrete at the joint, permits continuous curing of pavement, and provides protection for the joint until removed or depressed in preparation for the sealing of joints. Although sawed joints have been used successfully on many projects, excessive cracking has occurred in some instances. This is usually due to delayed sawing. When sawing cannot be accomplished without undue uncontrolled cracking due to unusual conditions, provisions shall be made for using inserts. Filler type joints may be approved for longitudinal contraction joints when it is demonstrated that these joints can be properly installed with vibratory equipment. The filler must be maintained in a vertical position and in proper alignment in the finished pavement. With regard to installation of insert type joints will be installed immediately after all machine finishing operations are completed. The machine for installing the insert shall have a vibratory bar that cuts a groove in concrete and simultaneously installs an insert in required locations. The intensity of vibration on the bar will be variable as necessary to form the groove in the freshly mixed concrete and to consolidate the concrete around the insert after it is in place. Inserts must be the proper depth for the concrete being placed because the load transfer between the slabs depends on the interlock of aggregate below the formed portion of the joint, and material that is not deep enough will not produce cracking at the proper location. Insert material shall be placed flush with the surface to not more than 1/8 inch below the surface. The surface of the pavement will be finished with a vibratory float. Hand floating will not be permitted. When finishing concrete after installation of the insert, an excessive amount of fine material must not be worked to the surface and adjacent to the insert. Excessive fines will cause scaling of the surface and spalling of the joint. With regard to sawing of transverse contraction joints, the method used, transverse and longitudinal contraction joints, shall be constructed to conform with details and dimensions indicated. Saw cuts shall be made to the depth indicated to ensure that cracking occurs as planned. Joints shall be constructed by sawing a groove in the hardened concrete with a power-driven saw. No definite time for sawing joints can be specified because of the many factors that may influence the rate of hardening of concrete, such as air and concrete temperatures during placement, ambient temperatures, weather conditions, curing and protection, cement contact, and mix characteristics. The basic rule for satisfactory sawing is be prepared to saw as soon as the concrete is ready for sawing, regardless of the time of day or night. During warm weather, when most pavements are constructed, the concrete usually will be ready for sawing about 6 to 12 hours after placing. Since concrete is placed mainly during daylight hours, a large portion of sawing will have to be done at night, and adequate lighting must be provided for this purpose. Although a clean, sharp cut is desirable, a small amount of raveling at the top of the saw cut is not objectionable when early sawing is necessary to avoid uncontrolled cracking. Sawing too early, however, will be guarded against to prevent excessive washing and undercutting of concrete in the joint. The proper time for sawing the joints will be determined for prevailing conditions on the job during each concrete placement. Since conditions may change from day to day, it is essential that the saw operator be experienced in sawing pavement joints. The sequence of sawing: transverse joints will be sawed consecutively in the same sequence as the concrete is placed in the lane. Sawing of alternate joints if the pavement is undesirable because concrete tends to tear away ahead of the saw cut when intermediate joints are sawed. This procedure also reduces the uniformity of fracturing of joints, which may result in excessive opening at some joints. Before sawing each joint, the concrete will be examined closely for cracks, and the joints will not be sawed if a crack has occurred near the joint. Sawing will be discontinued in any joint where a crack develops ahead of the saw cut. All areas of curing compound damaged by the sawing operation will be resprayed. A cord will be placed in the saw cut to retard evaporation of moisture. The special joint shown in figure 1 following for placing new concrete pavement adjacent to old concrete pavement requires special care. The concrete placed under the old pavement must be thoroughly vibrated and must not be placed too rapidly, or air voids will form under the old concrete pavement. Use of a water reducing admixture to improve workability may be helpful. Proper construction of this joint requires special inspection of construction technique. An alternate method of providing a load transferring joint when abutting old and new concrete pavements is to drill and grout dowel bars into the vertical face of the old pavement. Pavement protection is important. All vehicular traffic shall be excluded from the pavement for at least 14 days. As a construction expedient, earlier use of pavement is permitted for operations of construction equipment only as necessary for paving intermediate lanes between newly paved lanes. Approval for use of the pavements for construction purposes prior to 14 days may be omitted from contract specifications if unnecessary or undesirable for local conditions. Operation of construction equipment on the edge of previously constructed slabs will be permitted only when concrete is more than 72 hours old and has a flexural strength of at least 400 pounds per square inch. In all instances, approval for the use of pavement will be based on adequate provisions for keeping pavements clean and protecting pavements against damage. When appropriate, contract specifications may require that concrete be measured and paid for on a square yard basis. Whether concrete is paid for on a square yard or cubic yard basis, the unit price schedule for bidding purposes will be prepared to show separate estimated quantities for different pavement thicknesses that may be required. Figure 1 shown here illustrates special joints between new and existing pavement. And that brings us to the conclusion of this brief discussion of concrete pavements. I hope it has been of some interest and use to you and will permit you to move forward and address concrete pavement issues as you move forward. Thanks a lot. Bye.